Welcome to part 4 of my series of lectures on motion in a central force field. First, a quick recapitulation. We began by realizing that a two-body problem of two bodies interacting among each other with purely central forces can be reduced to an effective one-body central force field problem where the mass gets replaced by the reduced mass mu. And because angular momentum conservation told us that the motion had to be planar, we could use polar coordinates. And in polar coordinates, the two components of the equation of motion took this particular form. The second of these equations could be immediately integrated to give us theta dot into r squared as a constant. And since that constant happens to be the magnitude of the angular momentum over mu, we could just write down theta dot as L over mu r square. Using that, we could change the radial equation into a purely r-dependent equation, an equation in which theta has been completely decoupled. That's mu r double dot equals the actual force F of r plus an additional force-like term, which really is this term brought to the other side and often called the centrifugal force barrier term, L square over mu r cube. We also realized that this equation could be recast in the form of an energy conservation equation, which is half mu r dot square, plus an effective potential energy, which is a function of r alone, and the sum is equal to a constant E. This effective potential energy is the sum of the actual potential energy plus a term which is actually a part of the kinetic energy, half mu v theta square, but because of the fact that v theta, r theta dot, can be rewritten entirely in terms of r using this equation, we have a term which looks like a function of r and r alone, giving rise to this effective potential. In one of the lectures, we took a look at what kind of qualitative things we could say about the motion by looking at the way the effective potential behaves for various different kinds of potential. And then in the last lecture, we saw that not only could we make qualitative assertions about the motion using the notion of the effective potential, we could also make quantitative statements. In particular, we could reduce the solution of this equation of motion to just quadratures. This equation could be solved easily for r dot, which is dr dt, and since that turns out to be entirely a function of r and r alone, we could rewrite that equation in such a way that we could find t as a function of r by just doing an integral. And since this could be inverted to give us r as a function of t, the job of finding how the distance from the center changes with time has been effectively reduced to evaluation of this single integral. Well, r alone will not tell you exactly where the particle is. You will also need to know theta as a function of t, but that's also pretty straightforward. Once you know r of t, since theta dot d theta dt is just L over mu r square, which now is known presumably as a function of t, you can just integrate that to directly find theta as a function of t. So, the problem of solving the motion, finding out exactly where the particle is at a given time, essentially gets reduced to two integrals which can be evaluated. It is possible, of course, that the two integrals involved here may be very difficult to evaluate, but even if you could not possibly evaluate them in terms of simple functions, you could always fall back upon numerical methods, etc. to solve them. But in principle, the problem has been completely solved. Indeed, a problem which is often easier to solve by quadrature is evaluating r as a function of theta, that is, finding out just the orbit rather than the actual dynamics of the motion, just finding out the path the particle takes. And it's pretty easy to see that the two results that we stated above, that r dot could be figured out from the energy conservation equation and theta dot could be figured out from using L by mu r square, you could find out d theta dr rather readily, and integrating that would give us the orbit equation. And this is the orbit equation which we derived in the last lecture. We also talked about how to use this orbit equation to ask questions about whether a particular orbit would be closed or not, by figuring out whether the apsidal angle, the angle between the lines joining the center to the nearby apses, the point closest or furthest from the center, whether that angle was an rational multiple of pi or not. Now today, we will begin by using this orbit equation to solve for the orbit for a couple of very well-known standard problems. And I guess based on what we talked about in the previous lecture, you should be able to guess pretty clearly which ones those potentials are. They are, of course, the Kepler potential minus k by r and the three-dimensional harmonic oscillator potential kr square. So first, the Kepler problem. The Kepler potential is minus k by r, and that means the effective potential is minus k by r plus L square by 2 mu r square. So we can just change the orbit equation for this particular case into this particular equation, where we have made one special choice. We have chosen theta equal to 0 to correspond to a minimum of the distance. That is, the pericentron is the point, or rather the line joining the origin to the pericentron is the line from which you are going to measure the angle theta. So theta 0 corresponds to r min, and theta 0 has been taken to be 0. So this is our equation, and of course what we need to do next is to evaluate this integral by substituting the value for u effective r. And once you do that, this is the integral that you need to evaluate. Now this integral actually should be pretty easy to evaluate after the apsidal angle calculation that we did for the Kepler potential in the last lecture. In fact, we could just leave the details for you to work out because we have already shown you how to work this out. But still, let me just go through this again because this is a new lecture. First thing we do is get rid of the r's in the denominator by pushing one of the r's inside the square, which of course comes in as an r square. So this becomes er square, this becomes kr, this becomes minus L square by 2 mu. And then we take the coefficient of the highest power, that is r square, inside the third. There's only still one r left outside. We take that out, but for a bound orbit in a Kepler potential E is negative, so we take minus 2 mu E square root out. And once you do that, the quadratic part which is left under the third, that is minus r square minus k by E into r plus L square over 2 mu E, this is something we factorize into r max minus r into r minus r min. This follows simply from the fact that r max and r min, the two turning points, are exactly where E equals u effective r, that is where this factor vanishes. Once again, if you have viewed the previous lecture, this should be a pretty familiar step. And the next thing that we will do here should also be familiar from that. The substitution that we carry out. We take the ratio r max minus r over r minus r min to be s, and that essentially tells us that s plus 1 is directly related to r minus r min, and indeed it can be rewritten to give you r equals r min plus r max minus r min by s plus 1. So this of course gives us dr is negative of r max minus r min by s plus 1 whole square ds, and allows us to replace the square root here by root over of s, that's of course r max minus r by r minus r min, times r minus r min. So plugging all of this back into the integral, we see that apart from the L over root over 2 mu times minus e, what you have is the following. You have r max minus r min ds by s plus 1 whole square. That essentially is the dr apart from a minus sign. Then we have this root s, which is just this root s, into r minus r min, into r, which I have also rewritten in terms of s. And of course, this whole combination r max minus r min by r minus r min is nothing but s plus 1. So one of the s plus 1s just go away. And then if you multiply the s plus 1 through, you will actually get something which is very easy to figure out. It's going to be r min into s plus r max. So that's what that bracket is going to turn out to be. One more thing, what happened to the minus sign? Well, if you look at the limits actually were r min and r theta. So when you put in s equals this particular substitution, then when r is equal to r min, s actually diverges to infinity. And when r is some finite value depending on theta, you get s as the corresponding function of theta. So s of theta is just what you get when you put r of theta in here. So you had infinity to s of theta. The minus sign took care of changing the order of the limits. Of course, the plus minus sign, which is there from the original ambiguity in figuring out dr dt from the energy conservation, that is still, of course, there. But after you do all the cancellations, this integral becomes a pretty straightforward integral. Apart from this overall factor, it's an integral from s of theta to infinity of ds by square root of s times s r min plus r max. Once again, the next substitution that we do here should be pretty familiar from the last lecture, if you have viewed the last lecture. And even without that, it should be a sort of obvious thing to do here. You put in s equals r max over r min times tan square phi. And once you do that, the infinity here, for s equals infinity, tan square phi is infinite, so phi is actually pi by 2. That goes for the upper limit. The lower limit, whatever phi of theta you get, that is from s of theta, you get a phi of theta. That goes in the lower limit. In ds, you have r max by r min into twice tan phi into sec square phi d phi. That's the ds. The root s is simply this here. And s times r min plus r max simply becomes r max into sec square phi. And the great thing about that is every phi dependence cancels away. Of course, for the apsidal angle calculation, we had a 0 to pi by 2 here. But now you have phi of theta to pi by 2. So that's the only difference between the calculation I'm doing here and the calculation I did in the last video. So theta works out to be plus minus twice L by root over minus twice mu e, pi by 2 minus phi theta, with root over r max times r min in the denominator. And the important thing is r max and r min basically being roots of this quadratic equation, this equal to 0. Basically, it's a constant term here, r max times r min times minus r min is L square by 2 mu e. So, square root of r max times r min exactly cancels this factor. So, theta is nothing but plus or minus pi minus twice phi. Of course, what we need to do is to rewrite r as a function of theta. So, we go back in steps. This actually gives you phi as a function of theta. Phi is simply plus or minus pi by 2 minus theta by 2. We take that expression for phi, plug it back in our expression for s. This gives us s for a particular theta. R max by r min times tan square of this, which of course transfers to cot square of theta by 2. So r, now r we know how to write in terms of s. It's just s times r min plus r max by s plus 1. So we plug that in, we get r max, since s is given by this, r max into cot square theta by 2 plus 1 in the numerator, and of course r max by r min cot square theta by 2 plus 1 in the denominator. Now, cot square theta by 2 plus 1 is of course cosec square theta by 2, and if you divide the numerator and denominator both by that, this becomes cosine square theta by 2. This becomes a sine square theta by 2, and this simply comes out to be this. Well, This is still not a familiar form for the solution. For those of you who already know the solution, this may not be the form in which you are familiar to it. But using the fact that cos square theta by 2 is half into 1 plus cos theta, and sin square theta by 2 is half into 1 minus cos theta, this simply works out to be this expression. And so we can simply rewrite this as r equals a constant. If you just divide through by this in the numerator and the denominator, whatever comes in the numerator, you are calling r0. This becomes a 1, and this ratio is what you call e. And so this helps us to identify the parameters r0 and e with the maximum and the minimum distances. r0 is nothing but twice rmax rmin by rmax plus rmin. This formula looks very much like the reduced mass formula, but of course has nothing really to do with that. And e simply becomes rmax minus rmin by rmax plus rmin. These are equations which should be familiar to those of you who have already studied the solution of the Kepler problem. And we are going to derive this equation in an entirely different way soon. And after that, we are going to try to analyze what this solution actually means. But for the time being, just note that we have managed to solve for r as a function of theta here completely by just carrying out the integral. The other problem that we are going to solve using the same method is the problem of the 3D harmonic oscillator. And it should be pretty obvious to you by now, especially if you have listened to the last lecture, that the procedure involved will be almost the same. So I have just written down the basic expression here. Theta minus theta 0 is going to be this integral. Here I have just taken theta 0 to be the direction in which you have rmin. That is the angle which the line joining the center to the point of minimum distance makes with whatever axis you are using. And if you in fact use that as the axis, as we will do later to simplify the final result, that angle theta 0 is going to turn out to be 0. Now this time around, we are going to go over the steps a lot quicker and not go into as much detail as before, simply because the steps are very much the same as in the previous problem. Here the highest power is r squared. To get rid of this r square, you move with one factor of r as r square inside, and then take L over root over 2 mu out from here, and you get something very similar to what you had earlier, except that you have r max square minus r square into r square minus r min square in this case. And of course, this particular polynomial, the quartic, which is actually a quadratic in r square, just works out to be this, which can be factorized like this. And just one more extra step that is needed here, that wasn't there in the previous work, is that you have to make one further substitution, put r square equals u, which changes the dr over r here to du over u into 1 by 2. That's basically the only major difference. Of course, the limits also change. After that is essentially the same substitution, same bit of work, almost identical, and in the end, once again rather magically all of this cancels out. Of course, you have square root of r max square r min square here instead of square root of r max r min as in the Kepler problem, but otherwise it's more or less the same thing. It turns out that these two are exactly equal. So theta minus theta 0 works out to be this. So now the only difference, of course, is here you have an extra half which you did not have in that problem. So here phi of theta works out to be pi by 2 minus plus theta minus theta 0. And by plugging the formula back and going back to r, you simply get this expression. R max square minus r square by r square minus r min square. This is of course s. That's r max by r min, tan square of this quantity. Cos square theta minus theta 0. Just a simple rewrite from this gives you this. And now it becomes even simpler if you just choose theta 0 to be 0 and realize that what this is telling you is this is Sine square theta 0 minus y square by r max square equals cos square theta 0 minus cos square theta 0 plus x square by r min square. So this is simply an equation of an ellipse centered at the origins. Of course, those of you who know the solution to the Kepler problem would know that the solution there was an ellipse too, but there the center of the force was at one focus. If you don't know that, just hold on, we are going to discuss that in great detail in the next lecture. But this one is obviously the equation of an ellipse for which the center of force is at 0, 0, the origin. So that's one major difference between the two cases. Now, why is x coming with r min and y with r max? That's simple. That's because we had deliberately chosen theta equal to 0 to correspond to r min. That was the choice we had made. Theta 0 has been chosen to be 0 actually. So if you had chosen r max to correspond to theta equal to 0, of course what would have happened is that you would have got x square by r max square plus y square by r min square equals 1. Now, after seeing the details of the calculations above, it is possible, though I admit not very likely, that a viewer may go away with the idea that since we have chosen two potentials apparently at random and have managed to solve for the orbit explicitly in both the cases, explicit solutions may be quite common. I think it's way more likely that after seeing the details of the calculation and the somewhat intricate steps involved, one might go away with the idea that perhaps these are the only two potentials for which we can explicitly solve the integration. So the question that we have here right now is, although we have been able to reduce the problem to quadratures, is the quadrature something we can evaluate in terms of known functions? In the next few minutes, we are going to explore this question. Of course, we are not going to be able to answer this question for a completely arbitrary potential. So what we will do is we will stick to potentials of power law type or some combinations thereof, and try to see under what conditions we can evaluate the integrals involved in the solution. Let's take a look at a potential which is given by U equals some constant A times R to the power M. A power law potential as we had claimed to be what we would consider. One important point is that the product AM should be positive in order that this be an attractive potential. Now, we are going to focus on the quadrature for finding R as a function of time or time as a function of R. The orbit quadrature essentially follows the same basic ideas as you should be able to work out on your own after seeing this. So let me remind you that we will start with the energy conservation equation, rewrite that to figure out R dot in terms of the conserved quantities E and L as well as the actual potential U of R, which in this case is AR to the power M. Now, in order to help in figuring out the solution to the quadrature, remember this is basically dt will be given by dr divided by square root of 2 by mu E minus this whole bracket here. What we are going to do is we are going to start by making a substitution. Let's take R to be v to the power alpha, where alpha is some number that has to be determined. Of course, this means that R dot is alpha into v to the power alpha minus 1 v dot. And if we put that into our equation, we get alpha square v to the power 2 alpha minus 2 v dot square is twice E by mu minus L square by mu square v to the power minus 2 alpha, that's simply the 1 by r square that you have here, minus 2a by mu v to the power alpha m. That again is the r to the power m in the potential. Or after I divide through by this power on both sides, we get alpha square v dot square equals twice e by mu v to the power 2 minus 2 alpha. That's simply this power brought to the other side, minus L square by mu square v to the power 2 minus 4 alpha, minus 2a by mu v to the power alpha m plus 2 minus 2 alpha. The question is, under what condition can we figure out the integral dv by v dot, the square root of this side, which is of course dt, in terms of known functions? Now, the answer to that question, of course, would depend on what you consider to be a known function. So let us first begin by what we would call elementary functions, functions like cosines, sines, and so on. Now, this is a standard result from integral calculus, which may not be formally known to many of you, but if you have solved many integration problems, you would know that this is something which is essentially correct. An equation of this kind, v dot, is basically some polynomial in powers of v, although may have fractional powers as well, but still a combination of powers of v on this side, can be solved in terms of elementary functions like cosines or sines. If this equation can be recast in the following form: v dot is some power of v, some integer power of v, this is an important point, times the square root, of course there's a square root involved here, of a polynomial in v. And if you want a solution in sines and cosines, this polynomial in v should be a quadratic function. So, square root of a quadratic function in v times v to the power k, where k is any integer. If you divide dv by that to get dt, you can actually integrate this explicitly in terms of sines and cosines. These are actually standard integrals which you must have studied in high school. Now, let us take a look at the powers involved here and see under what conditions can this expression here take this particular form. Now these three powers, 2 minus 2 alpha, 2 minus 4 alpha, and alpha m plus 2 minus 2 alpha, must belong to the set 2k, 2k plus 1, and 2k plus 2. Which means that they can differ by at most 2. Now this will tell us quite a lot about possible values of alpha and m. Note that the difference of these two numbers, 2 minus 2 alpha and 2 minus 4 alpha, which is 2 alpha, can only be 2 minus 2 minus 1, 1 or 2. That comes from the fact that the difference is at most 2 and 0 is not allowed, because alpha equals 0 would simply mean that you are substituting a constant, r to the power 0, which is of course not a valid substitution. So alpha has one of these four values, minus 1, minus half, half or 1. Now let us take a look at these one by one. Now if you look at alpha equals minus 1, then 2 minus 2 alpha has to be 4, 2 minus 4 alpha has to be 6. Since these already differ by 2, they have to be of the form 2k and 2k plus 2. So now, the other power that we have, that is alpha m plus 2 minus 2 alpha, which for this particular value of alpha is obviously minus 1 into m plus 4, that is 4 minus m. Now the only possible values this can have could be one of the powers between 4 and 6. So it could be 4, 5 or 6. Any one of these choices would give me a result which is v to the power 4 times a quadratic in v, which of course after you take the square root becomes v square, an integer power of v, times the square root of a quadratic in v. exactly what you need to get a solution in terms of cosines and sines. So this tells us the possible values for m. Since 4 minus m can be 4, 5 or 6. This might imply that m can be any one of 0, minus 1 or minus 2. But note that 0 is not allowed, or rather 0 is too trivial, because if m were 0, we would really end up with a constant for the potential and no force whatsoever. Actually, m equal to 0 can also be thought of as a limiting case for a logarithmic potential, but we are not going to worry about that right now. So alpha equal to minus 1 only gives you m equals minus 1 and m equal to minus 2 as the two cases where you can solve the integration in terms of sines and cosines. Well, what about alpha equal to minus half? In this case, 2 minus 2 alpha is 3 and 2 minus 4 alpha is 4. Since we want the polynomial to be an even integer power times a quadratic, the only possibility for the other coefficient, alpha m plus 2 minus 2 alpha, that is 3 minus m by 2, are 2 or 4. And that means that the only allowed values of m given this particular substitution are to the power minus half as v, which allows, of course, solutions in sines and cosines are 2 and minus 2. Note minus 2 is making an appearance here as well. Alpha equals half proceeds in exactly the same fashion. Here 2 minus 2 alpha is 1 and 2 minus 4 alpha is 0. So to get an even power of v times a quadratic, the third coefficient, which is 1 plus m by 2 in this case, can either be 0, 1 or 2. Note that a linear function also qualifies as a quadratic. We want up to a quadratic here. Now that means that m can take values minus 2, 0 or 2, but we have already ruled out the value 0. So once again we have minus 2 and 2 as the two possible powers in the potential, which will allow solution in terms of cosines and sines with this substitution, that v is r to the power half. Finally, alpha equals 1, which is where you don't really need a substitution at all. V is the same as r. Here 2 minus 2 alpha is 0, 2 minus 4 alpha is minus 2. And so the third power, which is now m, can only be 1 of 0 or minus 1 or minus 2. And once again, 0 is not allowed, so m can only be minus 1 and minus 2. So finally, the upshot of all this is, if we allow all of these possible substitutions, the only possible power law potentials for which you get sines and cosines in the solution of the integral are powers of minus 2, minus 1 and 2. That is terms like 1 by r square, 1 by r and r square. Now, notice that in each of these sets, m can be minus 1 minus 2 or 2 minus 2, the same again, or minus 1 minus 2. You basically have minus 2 and 1 more. Which means that if you take the combinations a by r plus b by r square, that is the minus 1 and minus 2 together, and carried out the integral directly with v equals r to the power 1, you would be able to evaluate the answer in sines and cosines. Similarly, cr square plus d by r square also yields solutions in terms of sines and cosines. However, say a term like alpha r square plus beta by r will not be something you can solve in terms of sines and cosines. The fact that this 1 by r square term seems to be present everywhere, and you can add this term to a potential which already admits of a solution in terms of sines and cosines, and leads to a new potential which also admits of such a solution, is actually not an accident. It follows from a theorem which was derived by none other than Newton himself. And we are going to talk about this Newton's theorem a bit later on. Before we leave this particular topic, let us try to take a deeper look at this. We said that this particular equation can be solved in terms of known functions simply because the quadrature can be carried out in terms of sines and cosines in this case. But does that exhaust our list of known functions? Actually, the answer is of course not. In fact, integrals of the kind dv divided by v to the power some integer power times square root of a higher order polynomial are also pretty well known, provided the power of the polynomial involved does not exceed 4. These integrals lead to functions which are not necessarily considered elementary functions, but also pretty standard functions. If you have an equation of this kind, where v dot is v to the power k into square root of a polynomial up to the order 4, then the solution can be done in terms of known functions. These are called elliptic integrals. Now, delving into the properties of these elliptic integrals or elliptic functions will actually take us way too far afield, and we don't really want this to become purely a mathematics lecture. So, I will not really spend much time in talking about this particular kind of exact solution, but let me just illustrate how the argument would go in that case. Now, we would again look at 2 alpha, which is a difference between two of the powers that are there in the expression for v dot square. And since we can have polynomials under the square root which are at the most of the order 4, this 2 alpha can have a magnitude which is bounded by 4, which means it can have 8 possible values, -4 all the way up to +4 in integer steps, leaving out 0, for a reason we have already discussed before. So in each of these 8 cases, we can find a series of possible values of m. So this is essentially the same kind of argument that we used a while ago to handle circular function solutions, but given the fact that you have a larger number of values to deal with, the argument is going to be slightly lengthier. However, let me just show you the case for one of these values. Since alpha can be any one of these -2, -3/2, -1, -half, 1, 3/2 and 2, let us pick on alpha equals -2. Then 2 minus 2 alpha is 6 and 2 minus 4 alpha is 10, which actually tells us that our polynomial has to be of the form v to the power 6 into a quartic polynomial, and the other power, alpha m minus 2 alpha, that is 6 minus 2m, can be one of 6, 7, 8, 9 or 10. And this gives us possible values of m given by -half, -1, -3/2 and -2. Note that not only will these powers individually give you solutions in terms of elliptic integrals, any combination of them will also give you a solution which will involve an elliptic integral. So, a potential of the form a r to the -half plus b r to the -1 plus c r to the -3/2 plus d r to the -2 will provide us an analytic solution in terms of elliptic integrals. Let me point out that 1 by r square again makes an entrance here, and as I have already said before, that is not an accident. We will not talk about the other values of alpha any longer here. You can actually work them out yourselves if you are interested. And old textbooks like, say for example, Whittaker's book on dynamics will give you a full list of all possible potentials of this kind. But before we leave this topic of exactly solvable quadrature, that is, of being able to integrate this in terms of known functions, Let me point out that in this case, just evaluating the integral may not be the complete story. The integration will only give you t as a function of r. If you want r as a function of t, you should be able to invert this. And sometimes, even for rather simple potentials, this inversion can pose quite a challenge. To see this, let us take a look at the one potential that is of immense importance to us, the inverse square law force or minus k by r kind of potential. For this particular potential, we have already seen near the beginning of today's lecture that not only can we integrate the orbital equation, that is, we can get theta as a function of r, we can also invert that to get r as a function of theta, yielding a solution to the orbit. Let us now focus on the r as a function of time quadrature for this potential. That is, a solution to the equation r dot equals root over 2 by mu e minus u effective r, and that of course here becomes plus k by r minus L square by 2 mu r square. The whole thing is under a square root. Let me also point out that here we had a possibility of a plus or a minus sign, but we are going to take only the plus sign because we are going to assume that we are, for the time being at least, going towards increasing r. Maybe start at r min, going towards r max, but we want to find out r of t anywhere in between. Once we have figured out what happens here, the trip back from r max to r min is pretty straightforward, is essentially a reflection of that, and any further repetitions will be essentially very similar. So let's just focus on r dot being positive here. Now this immediately gives us the equation dt is dr by root over 2 by mu e plus k by r minus L square by 2 mu r square. And by doing something which should be familiar from what we have already done before, we take the 2 by mu and the e out in the form of a square root, simply because e happens to be the coefficient of the leading power. Here, of course, when I say leading power, I mean r to the 0. The other powers are r to the minus 1 and r to the minus 2. But again, I can't take out e. We are talking of bound orbits here, orbits which go from r min to r max. And for a Kepler potential, such bound orbits occur only when the energy is negative. So what we have taken out is mu into twice minus e. And we can get rid of the 1 by r square in the square root by multiplying through by r square inside the square root, that is multiplying by r, the denominator, and of course at the same time multiplying the numerator also by r. So we get r dr, and once you have taken the minus e out, you get minus r square minus k by e into r plus L square by twice me. This of course fits exactly our criterion that what we have here is a square root of a quadratic. Remember, that is exactly what you need for this to actually work out as an integral that you can evaluate in terms of circular functions. Let us now show you how that evaluation goes through for this. It's pretty straightforward. Again, something we have done before. Just rewrite this quadratic as r max minus r into r minus r min, keeping the sign minus r square in mind. And here r max plus r min is easily seen to be minus k over e, which is a positive number of course. K being positive but e negative. Of course, this also tells us what r max times r min is, but we will not need to use that right now. What we need to do now is integrate this expression for dt from time t0 at which we are assuming r is equal to r min to a time t at which r is equal to rt, and this is the integral that we need to carry out. Now the next step that we will do is essentially identical to what we had done while solving the orbit equation. In fact, you have already seen this substitution twice today. So what we will do is r max minus r by r minus r min, we are going to call that s, which tells us that s is actually related to r by r equals r min plus r max minus r min by s plus 1, or equivalently s into r min plus r max by s plus 1, which gives us dr by just focusing on this term works out to minus r max minus r min by s plus 1 whole square ds. And plugging this all into the equation, we get t minus t0 equals root over mu by twice minus e, which is exactly this term. When r is r min, s becomes infinity, so the lower limit should be infinity, and the upper limit should be whatever s corresponds to r of t, which you have called s of t. But the switch in the order of the integrals has simply occurred because of the minus sign here. I've just absorbed that minus sign by switching the order so that it becomes s of t to infinity. Now this is the r in the denominator, s times r min plus r max by s plus 1. This is nothing but dr, except of course for the minus sign. This square root here is essentially square root of s times r minus r min, so square root of s, and r minus r min can be rewritten simply as r max minus r min by s plus 1. Now the good thing is lots of cancellations occur. This one cancels with this, one of the s plus 1s cancel with this one, but not enough cancellations occur to make this really nice, which is something which happened when we were solving the orbit equation, theta in terms of s. It's still not bad. You end up with root over mu by twice minus e. After all the cancellations are done, you are left with one factor here, root s here, and s plus 1 whole square ds here. The next substitution that we carry out is not the same one that we did for the orbit, but again, it's motivated by the same basic idea. You just set s equal to tan square phi, which makes this sec square phi, and the whole thing of course sec to the power 4 phi, and this simply becomes tan phi. So we plug that in. Remembering to change the limits, the infinity becomes pi by 2, the s of t becomes phi of t, where tan square phi of t is s of t. And what about this thing here? This is s into r min plus r max. So s is tan square phi. So it's r min tan square phi plus r max. Root s is tan phi, as we said, s plus 1 whole square is sec to the power 4 phi. And in the numerator you have ds, which is twice tan phi times sec square phi. So once again, lots of cancellations. And once again, not enough. You're still left with the sec square phi in the denominator, which is not bad at all, because you can always multiply both the numerator and the denominator by cos square phi, and then this becomes a rather simple integral. T minus T0 is, apart from this factor, you have twice, which is nothing but this 2, r min sin square phi plus r max cos square phi, integrated with respect to phi. A very simple integral to calculate actually. Of course, this should not be a surprise. We had already figured out that this potential can be solved using circular functions. The integral can actually be evaluated exactly. So this is basically a very simple next step that to carry out, which is a familiar thing where we have used twice sin square phi is 1 minus cos 2 phi, and twice cos square phi is 1 plus cos 2 phi, to rewrite it in this manner. And once you carry all the terms together, this integral is pretty straightforward. R min plus R max integrates to R min plus R max times phi, and here I've just put in the limits. R max minus R min into cos 2 phi integrates to half of R max minus R min sin 2 phi, and once we put in the limits, and remembering that sin pi is 0, you actually get a minus sign because you're taking the lower limit here. This is what you end up with. So finding out t as a function of r is pretty straightforward. Of course, you don't have r here, but remember, r of t is related to s of t, and that is related to phi of t. So for a given r, phi is straightforward. What is not so straightforward, however, is solving this to find r as a function of time, simply because in order to solve this, we will first have to find phi as a function of t. Once we do that, the rest is pretty easy. From phi to s to r is a straightforward series of steps. However, to solve for phi of t for a given t minus t0, what you need to do is solve an equation which essentially says twice phi of t minus this twice is simply this 2 product, Rmax minus Rmin by Rmin plus Rmax into sine twice phi t equals a constant, which is basically an equation of the form theta plus epsilon sine theta equals beta. Once you figure a solution to this out, you can, of course, then put tan square of that theta as s and go on to calculate r. This particular transcendental equation, theta plus or minus epsilon sine theta equals beta, goes by the name Kepler's equation, because Kepler was one of the people who made use of this equation when he was trying to fit the actual motion of the planets to his calculations. Of course, he did not have a theoretical justification for this. His idea was based solely on observations. But it was a great thing that Kepler could figure out exactly how planets moved. And our more modern calculations, these are of course not very modern, these were done by Newton himself. But still, more advanced physics-based calculations give you exactly the same approach. We will have more to speak about Kepler's methods later, but what I wanted to emphasize here was the fact that although we could easily find out t as a function of r in this case, inverting that and finding r as a function of t may involve a step which involves solving a transcendental equation, something which we cannot really solve that easily. Today, with computers and numerical methods, it's really not a hard thing to do, but you have to appreciate that Kepler actually worked all this out, essentially by hand. Now, before we leave this topic completely, let me point out that there happens to be one case where this side is very easy to evaluate. That is the case where we want to find the time it takes from Rmin all the way up to Rmax. Notice that this is nothing but half of the total time period. If capital T is the time period, the time it takes to go from Rmin to Rmax and back is capital T. So this time that we are looking at, this t minus t0 value, is nothing but capital T over 2. Now, when r equals Rmax, our variable s, which remember is Rmax minus r by r minus Rmin, is simply 0. And since s is tan square phi, that tells us phi for that particular point at r equals Rmax is also 0. So we just plug in phi equal to 0 in this expression and most of it drops out. This one goes away, this drops out, and you are left with capital T by 2, the value of t minus t0 here, is square root of mu by minus twice e times Rmin plus Rmax into pi by 2. Therefore, t square is simply mu over minus twice e times Rmin plus Rmax whole square into pi square. These twos, of course, cancel each other out. At this stage, what we need to do is take a look at an expression that we wrote down earlier in a box, saying that we will need it later, which was, for this particular polynomial, it's easy to see that Rmax plus Rmin is minus k over e, or what we will need right now is e is minus k by Rmax plus Rmin. And therefore, plugging that in this expression, in place of e, we get t square is mu times pi square, this mu times this pi square, by twice k, and this Rmax plus Rmin that you had here goes up, and you end up with Rmax plus Rmin whole cube. Since Rmax plus Rmin for an elliptical orbit, the kind of bound orbit that the Kepler potential has, is actually twice the semi-major axis. So A is Rmin plus Rmax over 2. This expression is simply T square is 4 mu pi square A cube over K. So this is the famous Kepler's third law. T square varies as A cube. We had earlier used this law for the special case of a circular orbit to show that if Kepler's third law is valid, the force should be inverse square. But right now, what we have shown is that for a general elliptical orbit, T square is going to be proportional to A cube, where A is the semi-major axis of the ellipse. Plug it in, works out to be 4 pi square over g m1 plus m2 into A cube. Note that for our solar system, Kepler had said that the square of the time periods of the planets is proportional to the cube of the semi-major axis of their orbits. Note that this proportionality constant actually does depend on m1, the mass of a planet. In the case of solar system, m2 is the mass of the sun and m1 is the mass of the planet. So the T square by A cube ratio is not really a constant. It does vary from planet to planet. However, you can see that the ratio 4 pi square over g m planet plus m sun is almost the same for all planets, simply because m sun is so much bigger than m planet. Now, if you use current values of the semi-major axis and period of various planets, you see that the value, at least for the innermost rocky planets, is exactly the same. That's simply because all of these planets are so light compared to the sun that you are going to get the same constant. Actually, the constant is the same for nearly all of the planets. But Jupiter, for example, the most immense of the planets, actually has a value for this constant. Note here we are plotting r cube by t square, so it's proportional to m1 plus m2. Not inversely proportional as in our formula written down there. For Jupiter, this ratio is actually larger than that for the rocky planets. You have 7.504 as opposed to 7.496 on the average. Saturn is more, but not that much more. Now, what might come as a surprise is that Uranus and Neptune, both of which are actually lighter than Saturn, has values for this constant which is larger or comparable to even Jupiter. But that actually tells us that the two-body problem is not the end of the story for the solar system. You also have to take into account the effect of all the other planets. It is not really surprising that this effect is most noticeable for Uranus. Because remember, the fact that Uranus did not exactly obey the Newtonian trajectories calculated using basic mechanics, that led people to surmise that there must be another planet beyond Uranus. And that is exactly how Neptune was discovered. Similarly, Neptune's orbit showed discrepancies which could be explained only by the existence of another object beyond Neptune's orbit. This led to the discovery of Pluto, which today do not consider to be a planet, rather considered to be a dwarf planet. The point remains that Pluto was able to perturb Neptune's orbit sufficiently that two-body results were not exactly obeyed. Having said that, do note that despite the huge variation in the masses of all planets, you do see an agreement to up to 3 significant figures in each of these constants. We will have a lot more to say about the solutions for the Kepler problem. In the next lecture, we will begin with an alternative approach to the orbit equation, which, among other things, will allow us to calculate a force from an observed orbit and, in particular, will allow us to solve the Kepler problem in a much similar fashion. We will also discuss the basic properties of these orbits in quite some detail. Bye till then.